Okay, yeah, we didn't, I forgot to put that last week. Yeah, I moved the camera. I bumped the box, not too badly. Okay. Right, so today, oh, there's some more chat. What kind of traversal is it? Traversal? Okay. Right, and I have to put this on, airplane. And start, right, I have to put this on airplane. And start the timer. Good, we're going. Sorry, I'm gonna turn on the chat and look in if it's about this. What kind of question and answer? Can you be Mr. Klages during these? I'm not even sure if oh yeah, it's a virtual exam. So how do I make the question and answer go away? Okay. So last year I was pretending that I was this super relaxed professor, but okay, so that's recording. So today we're going to try to get through 3 topics, 2 of which are not super hard, and the 3rd of which is kind of tricky. But I did the course notes. So nobody wanted to write up the scribe notes for optimal binary search trees last year, so I ended up doing it. Although later, I wasn't going to write scribe notes for all those sessions that people didn't want to cover. So there are some topics that we have no scribe notes. So I'm going to check. I have my scribe notes on the laptop, so I can check this. Okay, so the first problem we're going to talk about is something called subset sum, which is a bit like knapsack, but easier. Okay, so for subset sum, you get, can people see the, yeah, okay. You get a bunch of numbers, say 2, 5, 8, 9, 11, 17, and then you get a target number, which let's say is 25. Okay. Why did I make angle works? Let's make this work. Okay, so this is an instance of subset sum. So these are just some numbers, and this is your target. And the question is, can you add up, can you pick a subset of these numbers that add up to this number? Okay, so that sounds, I mean, everybody sees that, right? Okay, I'm going to turn the chat on so I can see what people are saying. Okay. So, I mean, for this instance, you could just sort of eyeball it and say, yes, probably there are a bunch. Maybe there is more than one way, but at least I hope I didn't make a mistake. I picked a couple. So, but how are you going to do this? Now, actually, this problem is technically a Bloom problem. Okay, this is actually a hard problem. It doesn't look like that, and I'm about to teach you a dynamic programming algorithm for it, which runs sort of in polynomial time. How is this not a contradiction? Well, it's going to run in time polynomial in the size, in the number of numbers, which is fine. And it's going to run in time polynomial in this. Actually, it's going to have like a linear factor in terms of this. Now, remember that that we measure the size of how big is this instance? Well, it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 digits. So it's something like 10, and then, okay, you have the commas and stuff like that. But it's something like the number of numbers, and how much does each number, how much space does each number take, like logarithmic space to write down. I didn't actually need space 25 to write this 25. So the size of my input is not proportional to this. This is only contributing a logarithmic factor. So if I have a program that has a factor 25 in the running time, that doesn't mean it's really polynomial. It's polynomial in 25, but it's not polynomial in the size of the instance. So that's why this is a boom problem, but we're about to see a dynamic programming algorithm for it. So the key to dynamic programming is sort of figuring out what you want to compute at each step, right? So what is a cell of your matrix going to mean? What are you figuring out? And sometimes you need something. Sometimes you just need you need like, okay, what's the answer? The answer is going to be this. Okay, then I'm going to compute that for every sort of subproblem. But sometimes you need something. You need more information about subproblems, but not here, I think. Okay, so does anybody have an idea of what how many dimensions is our matrix going to have? So, okay, before I ask that question, I should tell you, you're only supposed to use each of these numbers once. In standard subset sum, it's a subset, it's not a sub-multi-set. Okay, you're not allowed to say list size by list size. Could you do it that way? Not sure how to do that. So list size by something, yes. So okay, to keep going, what we're going to have is this is going to, let's say this is 1, 2, 3, 4, 5, 6. What we're going to have is a matrix which is size 6, and this is where this gets not so efficient. It's going to be size 6. Why did I make this 25? That's annoying. Let's make this something smaller than 25. Let's make this 15. Okay, then it's kind of, let's make this 12. Okay. Just so that we don't have quite as much stuff. Okay, so this is going to be 6. And then this is going to be 5, 10, 15. Actually, maybe I'm going to need another one at the end just to be. Okay, so actually, maybe I'm going to need another one on top. Just to make this really easy to fill in, let's put another one in each end. Okay, so now this is 0, 0, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay, so you can just get all pair values. So you get no, but it's not pairs. It's subsets. So can you get 15 with, you don't get 15 with a pair. You get 15 with a triple. So, I mean, yes, you could do this by like considering every possible subset, which is 2 to the number of numbers, but that isn't even polytime in this thing, right? That's just horrible. So what we're going to do is Mij is a Boolean value, is true if, let's say that this is x1, x2, x3, x4, x5, x6, and let's call this thing t. So Mij is true if we can select a subset of x1 to xi that sums to j. And false otherwise. And I should have written this over here so I could write the program here, but okay. So can we choose a subset of well, nothing that sums to nothing? Yes, we can. Okay, I'm actually gonna fill this in red. So this is true, right? Everybody sees that's true. Okay, can we get a subset of rows? Yeah, okay, rows is right, rows is supposed to be the numbers, columns is supposed to be. So can we get a subset of nothing that sums to 1? No, right? We can't get a subset. A subset of consisting of nothing, of nothing, x1 to x0 is the empty subset. So this is false, and 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 this is false, 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 false. Did I start the timer? No. Oh, yes, I did. Okay, 13 minutes. Just making sure this is recording because I'm paranoid. It's recording. Okay. Okay, so now can we choose a subset of x1, the singleton set x1, that sums to 0? Yes, you don't choose anything. So this is true, and 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 this is true. No matter, like, if I said, oh, can you choose a subset of x1 through x6 that sums to nothing? You'd be like, yeah, I don't choose any. Okay, so now we have to figure out if you know. Oh, so usually I should have flipped this around. I've reversed the usual matrix. Now I'm doing sort of XY between the 0 row and 0 column. Okay. What is this cell asking? It's asking this now, okay, usually you count down, and I've accidentally done it counting up. Does anybody want to stop? And in the lecture notes, I'll do this properly. I'll switch it around. But let's say that this is, let's say that this is this is 0, 4. Okay, so this cell is 0, 4. This is M 0, 4. So that's asked. That should be true if we can choose a subset of x1 through x0, so the empty set, that sums to 4. We can't do that. we can't choose nothing and have it sum to 4. Right? Maybe we could choose a subset of bigger set and have it sum to 4, but we can't choose a nothing and have it sum to 4. So this is false. In fact, all of these are false. In the lecture notes, I'm going to turn it upside down, so it's not. Now I'm doing x, y for some reason. Okay, so how are we going to? Yes, we can choose 4, 0. 4, 0 is, can I choose a subset of x1 through x1, x2, x3, x4 that sums to 0? And you're like, yes, I can. I don't choose anything, and then it sums to 0. So this is all true. You can always choose a subset that sums to 0, and this is true, and then the rest of the row is false. Okay. So now the question is, if I have, if we have, that doesn't look like an M. M I minus 1 J M I minus 1 J minus 1 M I J minus 1. Can we fill in Mij? And the answer is not exactly. Okay, we don't just need these. Okay, we did for edit distance. Remember, edit distance, we just looked at the blocks above and to the left and to the left. But now this isn't going to quite work. Okay, because now actually what we're going to say is, if we have we need M. Unfortunately, after I erase, oh, foo. This is a little bit damp, so I'm just going to get a piece of paper. Right. So what you actually want is to work out Mij. You actually think, well, I can work out Mij. If you think about it, well, either you take xi or you don't. Okay, right? So this is going to be. Don't think about just the stuff above and below. But if we take, take xi, then we can get some j if we can get some j minus xi from a subset of x1, xi minus 1, right? So if we decide to take xi, then, so this means that if we take xi, then Mij equals mi minus 1 j minus xi, right? But that's not the only option we have. If we don't take xi, then we can get j if some j from x1 xi, some j from x1 xi, if we can get some j from x1 xi minus 1. So actually, I should have written this in red so that it stands out. So I is the number of elements in the subset, and j is not, well, j is the target value at the moment, right? Is the target value for that cell. It's not necessarily the target value for the whole instance. Because when I'm filling in this cell, I want some 7. When I'm filling in this cell, I want some 10. Only when I'm filling in this cell do I want the, well, this cell or 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 this cell. Do I want some 15? Okay. So the thing is, if we take this one, we can say, well, we can get some mij is true. If we can get some j minus xi from from x1 to xi minus 1, or mi minus 1, or if we can get some j from x1 to xi minus 1, then we don't need xi, right? So this is mij is true, is the disjunction of these two things, okay? So you say, if one of these two things is true, then this is true, otherwise it's false. Good. Okay, so this is an or. Can people read that? Okay. So let's just sort of fill this in a bit. Actually, I'll leave that there. So, what is now the, oh, I forgot to announce. If you take j and you subtract xi and it's negative, then we're just going to assume that the answer is false. Okay, that saves me having to write a load of falses over here. Okay, so what is M11? So that's asking us, can we get, so M11 is asking us, can we get a subset of x1 that sums to 1, exactly 1? No. Okay. So this is going to, but instead of just thinking about it, we're going to do this automatically and say, okay, well, what is mi? This is true if we can get some minus 1 from the empty set, right? So we're here, which is x1, but then we subtract 1, so we're asking about the empty set, but it's over here. It's minus 2. Sorry, it's minus 1, because we're asking if we can get j is 1, x1 is 2, and so we can't get this. This would be m0 minus 1, and that's false. And then we're asking, okay, well, in that case, can we get some 0? This is m0, 1. And so we look here and we say, no, that's false too. So this is false. Okay. Now, what about, yeah, well, this is maybe more interesting. This is asking, can we get exactly 2? Can we get some 2? Okay. What is this asking? This is M2. I need more space. This is M1, 2. So M1, 2, we ask about M0, 0, right? Because, no. M1, sorry. Yeah, okay. I is 1, so we're asking about M0 and 2 minus x1 is 0. Or M0, 2. Well, this one is true, and M0, 2 is false. But it's an or, so this is true, so this is true, right? It says, yes, we can get a subset summing to 2 from just x1 because x1 is equal to 2. Haha, isn't this fun? Okay, so can you, we're going to erase some of this stuff. And I have to start the timer again. Okay, so we're going to erase some of this stuff. And then we're going to try to write a little program to do this. To fill in this matrix. Do we want to do another of these, or do people get this? Does that say that mij equals mi minus 1, j minus 1, or mi minus 1j? This says, okay, I'll write this bigger. When we get to the program, so you write mi0 equals true, right? So that says this column is true. M0j equals false for j greater than 0. So that says that this row is false except for this one. Okay. Now, for I equals 1 to what are we going to say? Let's say that this is M. Let's say that we have M elements. M is the number of elements that we're allowed to choose from. For J equals 1 to N. Yeah, okay. Now we get this thing. Mij equals M I minus 1 J minus Xi. Or M I minus 1 J. I minus 1 J. So this is saying we take Xi, and so we want to get exactly the sum J minus Xi using x1 through Xi minus 1. And this one is saying we don't take Xi, and so we want to get sum exactly J from x1 to Xi minus 1. Okay, so it's N4. N4. N4, N4, print oops. I'm using big M as my matrix and little m as my array. Let's call this A, just so that people can't get confused. Well, in the lecture notes that people won't get confused. In the lecture, people may get confused by me switching letters. I was writing the lecture notes for edit distance yesterday, so I wasn't preparing this lecture. Okay, for print A, M, N. Okay, so what is Mn? Can you get sum exactly N, which is the target? So now this is N. Sorry, not T. N. Can you get sum exactly N from a subset of the elements? And that's exactly the question we're trying to answer. How did we define M? It's not J M minus 1 J minus 1, but it's not J minus 1. It's J minus Xi. Remember I said before when we were doing edit distance, we just had to consider the stuff that's above and to the left, but okay, let's fill in some more of these so people can see what's happening. Okay, so can we get some exactly 3 from subset 1? So this is all going to be false, actually, because it's asking, because actually the only sum we can get from one element from x1 is x1 or 0. Okay, so it's true we can get from x1 just choosing a subset of x1. If we choose x1, we get x1. If we don't choose x1, we get 0. Okay, so now can we get a sum of 1 from x1 or x2? No. Okay. I'm just filling this in quickly so that people can have a demonstration, because otherwise we're going to run out of time. Can we get sum exactly 2 from a subset of x1, x2? This is getting a little bit harder. Yes, but let's look at this program. So what we do, we look here and we say, okay, so Aij, so we're looking at A, 2, 2. So we look at A1, and 2 minus x, so if we decide to take x2, then that's a 5. So we're trying to get some minus 3 from just x1. So that's not going to work. So this one is false. But this one, then we say, okay, so that was false. But then can we get some 2 from just x1? And we look and we say, okay, so this is going to be a1, 2. So this was a1 minus 3. This is not going to work. This is 1, 2. So can we look at 1, 2? It's a true. We take the OR of a false and a true, and it's a true. Okay, now can we get some 3? So we look at, if we take 5, this is going to be a minus 2. That's a false. Okay, if we don't take 5, we're asking, can we get some 3 from just x1, and it's a false, so this is a false. This one, same thing, it's going to be if we look over here, it's minus 1, so it's false. If we look down, it's going to be false. Now here, if we look down, it's a false, but if we look right, we're trying to get some, if we take x2, which is a 5, then it leaves us trying to get 0 from, it leaves us trying to get 0 from just a subset of x1. Can we do that? Yes, it's true. Look, it's true. It's right here. We just don't take anything. So this is true. So how about 6? So we go down 1 and we say, no, we can't get subset of, we can't get some 6 from just x1. So this is a false. We look over here, right? We're going over 5. We're going x2 over 5 and down 1, and it's a false. So this is a false. Now here, we look down 1, it's a false, but we look over 5 and down 1, and it's a true. So this is true. Yes, we can get a sum of size 7 from x1 and x2 because we take both of them, right? This true came from here. It says we're looking over here because we're taking x2, which is 5, and then we're saying, okay, can we get a sum of 2 from just x1? And the answer is yes, because we just take it because it's equal to 2. Is this another way to solve this problem? This is a boom problem. I mean, it's NP hard to do subset sum. This is actually not bad. I mean, the fact that we can do it in something called pseudo-polynomial time, which means that it's polynomial if the instance is represented, it's polynomial in the size of the numbers. So subset sum is NP hard in the weak sense. So actually, it's not that bad, really. Like filling this thing in, people think this is a cute trick. And besides, you just write this little program. The computer is going to do it for you. So we're just going to do like some more of 8. So we look down. This is a false. We look over here. 1, 2, 3, 4, 5, and we look down. This is a false. And so actually, these are all going to be false because even if we take both of these things, it gives us some of those stuff. So I'm just going to fill this in, and you're going to believe me that if we look down, one, then we're going to see a false. And if we look over 5 and down 1, we're always going to see a false. Okay, so now 3. Can we get some exactly 3 from x1, x2, x3? Well, let's see. If we take it, we look over here 8 steps. So we look at minus 7, 2, that's a false. And we look down 1, it's a false. So this is false. Here we look down 1, it's a true. So we also have to, like, if we took x3, it'd be way over here, and it's a false. Here we look over here, it's off the side of the matrix, so it's false. We look down, it's a false. Here we look over, we're off the side of the matrix, it's false. We look down, it's false. Here we look down, it's a true. We look over here, it's still off the side of the matrix. But this is a true because of this. 6, again, 6 minus 8, it's off the side of the matrix, but we look down, this is a false. Here, it's off the side of the matrix. We look down, it's a true. Here, we look down, it's a false, but we look over 8, 1, 2, 3, 4, 5, 6, 7, 8, and we look down and it's a true. Can we choose a subset of x1, x2, x3 such that the sum is 8? Yes, we just take x3. So 9, we look down 1, it's a false. We look over here and down 1, it's a false, it's a false. 10, we look down 1, it's a false. But we look over here, 8, and down 1, it's a true, so the answer is true. How do we get 10? We take x3, which is 8, and then we try to get a subset that sums to 2 from x1 and x2. And how do we do that? We just take x1. Okay, so that's why this is true. So now 11, this is a false. We go over here, 8 to 3, we look down, this is a false. 12, this is a false. We look over here to 4, it's a false. 13, we look down, it's a false. We look over 8 to 5, we look down, it's a true. So this is a true. Can you get a subset that sums to 13 from x1, x2, x3? Yes, you take x2 and x3. 14, you look down, it's a false. You look at 6, you look down, it's a false. 15, you look down, it's a false. You look over 8, 15 minus 8 is 7. You look down, it's a true. So there is a way to take a subset of x1, x2, x3 that sums to 15. Let's take all of them, right? People could fill this in manually, I hope, believe. I mean, you just follow this. It seems to actually be working. Which is not guaranteed because it's quite easy to mess this stuff up if you're on your feet in front of a class, even if the class consists of only 20 people, like less than a fifth of my students actually show up. But it does, you could program this. It's not that hard. I'm sure you could figure this out. Okay, so let's move on because we are going to run out of time because optimal binary search trees is going to be really hard. Okay, so we've used 25 minutes for, that's not that bad. Okay, where did my paper talk? Because I have to, okay, so that was subset sum. NP hard, but you can fill it in, but the size of the matrix, well, the dimensions in the matrix is linear in this instead of logarithmic. So that's why this program doesn't show that P equals NP. Clink does not equal boom because of this. Okay, people understand, right? I take it, the laughing LOL. I will take it that people are. So this was a little bit trickier than edit distance in one way, which is we're not just looking we're not just looking beside us, we're actually looking over at another part of the matrix. So now let's do knapsack, which is also NP hard, but also NP hard in the weak sense. Which means that we can give a dynamic program for it, which runs in time polynomial in the size of the stuff. What is the key number in the instance? It's the capacity of the knapsack. So I forget the instance we had of knapsack. So that was subset sum. I'm not going to write it. I trust everyone can write who knows how to spell subset sum. Okay, everyone knows how to spell knapsack as well, but I'm just, and if in the notes I accidentally write backpack, it's the same thing. How many people in the class? We've stopped hemorrhaging students. We lost like 60 people. I think we've lost 60 now, but we're still slightly over 100. So technically, I shouldn't complain. We've lost 60, but we still have like 106 or something. This is not as bad as last year. Last year I lost 82, but I still had 99 people show. Okay, technically I lost 84 because 2 people didn't show up to write the final, but then 99 people actually wrote the final. So I got it down into double digits. But actually now Zoom just sent me a message saying that now for free, they're going to upgrade my webinar license to 500 participants. Why they didn't do that a month ago, so I didn't have to pay so much, I don't know. But okay. But now I don't think I'm ever going to get a class of over 100. So, okay, knapsack. So knapsack, remember now we're not trying to get a sum of exactly something. We don't have to exactly fill the knapsack. So the knapsack looks like this, and we have some items. We have a bunch of things that have weights, and we're trying to pick, so the knapsack has capacity C. Let's say the knapsack has capacity N, just for consistency. And we have M items. And we're going to do basically the same thing with profits and weights. So now, what are we going to do? We're going to do a matrix. So we want AI. So let's say that these items are x1 to xm. So we want aij max profit. We can achieve, no. This is going to be from x1 with weight j. Okay. So you have to. I do know this, but switching from problem to problem, I have to try to remember exactly how this goes. Okay, so I think it's the maximum profit we can achieve from x1 to j with from x1 to xi with weight j, exactly j. Okay. Now at the end, this means we don't just get to look at one corner of the matrix, because if we look at xmn, that's asking how much profit can we get exactly filling the matrix, exactly filling the knapsack. And it might be that you can get more profit, not quite filling the knapsack. So in that case, what you've got to do is scan scan the top row and find the maximum. Actually, row, column, something like that. It'll be correct in the lecture notes. So let's choose something a little bit smaller this time. we could do the same. Okay, we could do, what was it? No, let's not do a matrix that big. Let's just make it say the profit weight pairs are 2 profit 1. Weight 3 profit 4. Okay, so this is weight profit. Okay, so let's not write up there. Weight profit pairs, weight 3 profit 3. And let's say, okay, let's just make it 4 and profit 5. Okay, and let's say that the capacity of the knapsack is 8. Okay, capacity, so let's say n equals 8. So this is an example. This is in general capacity n. So let's say that these are our items. So actually, okay, our items are weight profit pairs, profits and weights and profits. Okay, so this is going to be weight I, profit I. And this is 2, 1, 3, 4, 3, 3, 4, 5. And let's say capacity is 8. Okay, so once again, we write the matrix. How many of these things do we have? We have 4. And now we remember that actually we want this extra row and column because it makes the base cases easy. So this dimension is profit. This dimension is weight. And this dimension is size of the prefix we're considering. So I'm going to write last element. Okay. Actually, I'm not going to write that because it doesn't leave me any space. So this is 0, 1, 2, 3, 4. So once again, I'm reversing things. It will be normal matrix coordinates in the notes. This is 0, 1, 2, 5, 6, 7, 8. I don't think we're going to get all through. Just going to make sure that's recording. It's recording. I don't think we're going to get all through optimal binary search. I don't know how. I was looking at the notes from last year. Last year, I taught optimal binary search. I taught edit distance, and then I taught optimal binary search trees in the same lecture, and I did it on June 3rd. How did I get to this stuff in 1 month? That must have been a crazy summer. It's because I was making other people write scribe notes. I was not doing the lecture notes. That's how. So I was having an easy time, and the students must have been having it really rough. Okay, so can we? The max profit we can achieve from xi to x1 to xi with weight exactly j. So this actually doesn't actually make any sense, because we can't we can't get weight 1 with an empty subset, right? So this is not defined. So we're going to say, what's the with weight 0 and subset of size 0, we can get profit 0. This is not defined. Now, what we're going to want is, again, to compute Aij, let's suppose we take xi. So if we take xi, then the max profit we can get okay, so this xi is the pair, right? So we take that. The max profit we can get with weight exactly j is a I minus 1 j minus w sub I, right? Because now I'm telling you, you take xi, so you plus pi. So you take xi. So I'm telling you, you have to get weight exactly j, and that's going to include xi. So you have to consider, okay, what can you now get? You get the profit from xi. But now you have to think, what's the max profit you can get with exactly weight j minus the weight of the thing you just took, the weight of xi, wi. Well, you have this computed, right? Because it's sort of to the left. So if you take xi, then aij equals this. If we don't take xi, then the maximum profit, so this is defined as the maximum profit we can get taking taking some subset of x1 through xi minus 1, achieving this weight, and then when we take xi, we get weight exactly j, and we get this plus pi. So if we don't take xi, then the max profit we can get with weight exactly j is a I minus 1 j, right? Because if you don't take xi and you have to get weight exactly j, then you better get weight exactly j from x1 through xi minus 1. Okay, so we have these two options, and we're going to take the max of these things. So now I'm going to write. So we cannot achieve, incidentally, what is, with weight exactly 0, what is the maximum profit we can get with each of these is 0. Because assuming that the weights are positive, the only way you can get weight 0 is not taking anything, and then you get profit 0. Okay, so we're going to say, okay, A I0 equals 0, and A0J equals, well, not really defined, because you can't get weight 3 without taking anything, exactly 3. So equals question mark for j greater than 0. Okay, so now for I equals 1 to m, for j equals 1 to n, Aij equals max of this, A I minus 1, J minus Wi plus Pi. Can you read this, or is it too small? Is anybody there? 2 people who disappeared. ITD good, readable, yes, is good, okay. Or the other thing we can take is we decide, so this is, you say, well, this is if you take it and you can get more, and then the other thing is you don't take it, and you can get I minus 1 J. I just realized I'm sort of saying this stuff and I'm standing in front of the board, because this is why I like having these big classrooms with lots and lots of blackboard space where you can like write and then you can stand off to the side, and I'm not standing in front of what I just wrote. The only way I could not stand in front of what I just wrote is okay, so then N4. And N4. But now we can't just do this thing where we say print AMN, right? Because print AMN is going to tell you the maximum profit you can get exactly filling the knapsack. We don't want that. So we want to print max. I don't need an extra bracket here. I do if I were writing C. Max, I'm going to put a curly brace because this is a set. Max over J of A MJ. Okay. So this is saying, okay, now I consider the maximum profit I can get from any subset of the things, so x1 to xm, but I don't care how much they weigh exactly, I just want the profit to be maximum. So it's taking the maximum profit you can get over the top row, which will be the bottom row when in the lecture notes when I'm sticking to normal matrix coordinates. Okay, so let's fill in some of these. Okay, so what can we get? What's the maximum profit we can get with from x, taking x1, trying to get weight exactly 1? This is not defined because we subtract, right? This is I minus 1, so that's fine. But j minus wi is 2, so we're over here, we're off the matrix, this is not defined, okay? Or ai minus 1, j, this is not defined either, so this is not defined. Okay, here we're trying to get weight exactly 2, and from a subset of x1. Just x1. Okay. So let's okay. We say I minus 1 down here. J minus Wi. W1 is 2, so we're here. So we're saying, if we take X1, then the profit we can get from not taking anything is 0. It's actually defined, it's 0. So we would get weight not equal. So if we don't take it, so if I tell you, you have to get weight exactly J, and you decide not to take the item, then you had better get weight exactly J from some item or a subset of items that's not that's up to xi minus 1. So here, if we're looking here, we're thinking, okay, this is I minus 1, you go down, and then you go to the left, Wi, which is 2, so you're over here. So you think, okay. And then you add Pi, which in this case is 1. So here it is a 1, okay? The maximum profit you can get from X1 with, how is it 12:41? I have 13 minutes. Okay, it doesn't look like I'm doing optimal binary search trees today. How did we spend, the little camera is not recording, 3. The little camera stopped? No, the little camera is still recording. I forgot to start the timer. Okay. But how did, it's 12:40? Okay, so we have 13 minutes left. That's going to be enough to do knapsack, but it's not going to be enough to do optimal binary search trees. I can sketch them. Sine x, cosine x, what? Sine x, what? Okay, so let's do this. Let's just keep going. So 3, we're going to drop down and go over here. This is not defined. If we take it, if we don't take it, we just drop down 1, right? So this is not defined either. So in fact, we can fill in the rest of this because there's no way to get any of these weights using selecting or not selecting, just something with weight 2. Okay. So here we say to 1, well, we can, if we take it, then we're dropping down and going over here, but then we're off the side of the matrix, so that's not defined. And if we don't take it, we're just dropping down, and so it's not defined. If we take it, we're dropping down and going off the side of the matrix, so it's not defined, but if we just drop down, it's 1. So this is a 1, right, because we're taking the max. So what does this mean? It means the maximum profit we can get with a subset of 2, 1, and 3, 4. Remember, it's weight profit. The maximum profit we can get from a subset of 2, 1, and 3, 4 that has weight exactly 2 is 1, right? Because we can only take this one. Okay. 3. So if we go down and over 3, we get here. So it's defined, okay, so we have the option of taking x2, which has weight 3, and that would mean we would get profit 4, because it's 0 plus 4, or we can not take it and drop down and try to get weight 3 from just x1, we can't do that, so this is a 4. Okay, here we can drop down and go over. and it's undefined, or we can just drop down, it's undefined, this is undefined. There's no way to get a subset of weight exactly 4 from these two. Then here, we can drop down and go 1, 2, 3. So this is a 1. So it's then we add the profit 4. So we could get 5, or we can just drop down and we get undefined. So the max is, so actually I shouldn't have put question mark, I should have put negative infinity. So then the max actually makes sense. Okay, so this is a 1 plus a 4, so this is a 5. So think of the question marks as negative infinities. Then here it's 1, 2, 1, 1, 2, 1, 2, 3. It's undefined. Just down is undefined. There's no way to get weight exactly 6 from these, from weights 2 and 3. 7, 1, 1, 2, 3, undefined, down, undefined. 8, 1, 1, 2, 3, undefined, down, undefined. Okay. Here, 3, so it's down, 1, 2, 3 off the side of the matrix, just down, it's undefined. Here it's down, 1, 2, 3, it's off the matrix, but down is 1, so it's 1. Here it's down, 1, 2, 1, 2, 3, it's 3 plus 3, 0 plus 3 is 3. Or we look down and we see a 4, the max is a 4. Right? So what is the max profit we can get from the first 3 of these? We weight exactly 3. It's taking this one. It's not taking this. Okay, then here we go down and we get 1, 2, 3. It's undefined. We just go down, it's undefined. Here we're down 1, 2, 3 is 1, so it'll be a 4, right? Because we're adding the profit 3, so it's either 4 or it's 5. The max is a 5. Right? Because what is the maximum profit we can get from these 3 things with weight exactly 5? Well, it's going to be choosing this one and this one, right? Not this one, because this is more profitable. So we get a 2 plus 3 is a weight exactly 5, and the profit is 1 plus 4, weight exactly 5. Okay, here we go down 1, 2, 3. So it's a 4 plus a 3, that's a 7. And down is undefined, so the max is a 7. Ooh, what does that mean? Well, how much profit can we get with weight exactly 6? We can take this one and this one, so it's weight exactly 6, profit is 7. This, so this one is going to be down 1, 2, 3, undefined, down is undefined. We can't get weight exactly 7 from these 3 things. And now down 1, 2, 3 is a 5. So 5 plus 3 is 8. We're down, so this is 8. Okay, so maximum profit we can get with, so yeah, I'm gonna have time just to finish off this tiny example. And then I can't believe this was supposed to be half a lecture, not a whole lecture. We're behind. We must go faster, more material. That's sort of, I'm kidding. But I do have to squeeze in optimal binary search trees somehow. Maybe on the assignment. That's also sort of maybe a joke. I did it on the assignment last year. Okay, well, the first year I was here. The year that like lots of people didn't like me. Okay, here 4, it's off the side of the matrix, down, it's undefined. You can't, well, still can't, okay. Down, it's off the side of the matrix, 1. Down, it's off the side of the matrix, so it's a 4. Down, 1, 2, 3, 4. It's a 0, plus profit 5. This is, so max of 5 and negative infinity is 5. This, 1, 2, 3, 4, undefined, down it's 5. This is down 1, 2, 3, 4. It's a 1 plus 5 is 6, but this is a max, it's a 7. This is down 1, 2, 3, 4 is a 4 plus 5, it's a 9. Down it's undefined, right? And here it's down 1, 2, 3. 1, 2, 3, 4. It's undefined, and down it's an 8. So if we just reported the top, we have 5 minutes. If we just reported the top right corner, it would be like, yes, if we fill the knapsack exactly, the max profit we can get, we're down to 16 people. The max profit we can get is 8. And how would we do that? Well, the capacity is 8. We would probably, the only way we can get weight capacity exactly 8 is 2 plus 3 plus 3. But if we don't quite fill the knapsack, we leave, we can stuff in 1 more kilo, then the profit is 9 because we get, how do we do this? It's, so we take this one because 1, 2, 3, 4. We take this one, we take that one. Yeah, okay, we take this one and that one, okay? We take this one and go to the 4. We do not, if we took x3, it would have been 3, but the max came from here. And this is, this we get the 4 from here. So we take this one and this one, we get weight 7, but we get profit 9. So when we scan the top row, which takes 1 year time, we get the max. So when we print max over J of AMJ, we print 9, which is, that was exhausting. Does everybody see how to do this now? My remaining 16 students, sort of. Don't worry, you'll get practice. I'm going to put it on assignment 5. You can always go back over the video. So the lecture notes should be better because I was accidentally like flipping. We should have been working downwards in order for I and J to make sense. How you derive the algorithm. Okay, so we have 2 minutes. So remember I said, when you're considering the subset x1 through xi. Your 2 options are, you take xi. Okay, in this case, if you take xi, so you're trying to fill in some cell of the matrix. And aij, now the magic is you have to choose aij correctly. Okay. So if you say it's the max profit, if you say it's the max profit we can get with weight up to j, then life gets hard. But so in this case, we're going to say, okay, it's the max profit we can get with weight exactly j. So you have to choose what aij is supposed to mean. You have to choose that right. That's the magic. I mean, people still publish dynamic programming algorithms. And the reason that we don't just say like, oh, this is easy, anything you can do with dynamic programming, we just plug it into this template. No, it's because you actually still have to think about, okay, exactly how many dimensions does my matrix have, and what is each cell going to store? So in this case, you say, okay, aij is going to be the maximum profit we can get from x1 to xi with weight exactly j. So now you're thinking, okay, so once we've decided that, you think, now if I take xi, then I'm going to think, so what is my budget of weight left? Well, it's j minus xi, right? Because if I decide, like my backpack, I've decided I want to fill my backpack with exactly 15 kilos. And I'm going to take this 5 kilo watermelon, which has profit 2. So I've decided I'm going to take that. So then I'm trying to figure out the maximum I can get in my remaining budget of 10 kilos, plus the 2 I'm going to get from the watermelon, right? So that's how you say it. So if I'm looking at the watermelon and I say, okay, I'm going to imagine, suppose I take the watermelon, then I want to fill up exactly 10 kilos, and I want to get the maximum profit from that, from the stuff that comes before the watermelon. If I don't take the watermelon, then I have to fill up, I've decided I'm going to fill up exactly 15 kilos, but only from the stuff that comes before the watermelon. I'm not going to include the watermelon. And then I don't get the 2 from the watermelon, I just get the profit from that. So that's, in the first case, it's the 2 from the watermelon plus the maximum profit of I minus 1, 10, the maximum profit I can get of the things before the watermelon with capacity, with weight exactly 10. If I don't take the watermelon, then I just say, okay, then I have to try to get weight exactly 15. So I'm looking for the maximum profit I can get with weight exactly 15 from items that came before the watermelon. So once you've decided what your matrix cells are, then the rest is not so bad. Except, so now I'm over time, and I'm down to 14 students, except optimal binary search trees are actually quite tricky. But I've already planned what we're going to do for the rest of it. I'm going to have to pack the next lecture. But I'm getting vaccinated, I'm supposed to be, on Sunday. So I might pre-record Monday's lecture. Okay, I'm going to stop recording now. I might pre-record Monday's lecture, and then I can go super fast and do optimal binary search trees and longest increasing subsequence in the same lecture. Not sure that's a hugely good idea, but I can try. Because I think from what people have told me about what this vaccine does to you, maybe I'm not going to want to try to do that on Monday in a live lecture. Also, that's the problem. Like I sprained my elbow last week, so my arm is already sore. It'll give you magnetic powers. Well, that's cool, but I think the little camera is metal, so that would be even harder to set up. Okay, thank you for hanging around 3 minutes overtime. I hope you understand at least subset sum and knapsack, and now you're starting to get the feel for how dynamic programming works. Good luck with assignment 4. Assignment 5 will be coming out soon, but assignment 5 is not going to be due. Oh no, assignment 5 is not going to. So because assignment 5 will maybe not be coming out on Friday. Yes, it will, but it will involve stuff that you don't know yet because I want to pack in Monday's lecture onto assignment 5 as well. Because then we can do like one assignment for dynamic programming and then move on to completeness. Okay. Any more questions? Any concerns? Anything? No. Ciao. Have a good weekend. Take time. Oh, okay. Thank you. Cheers. Stopping recording now. Yes.